next lecture on normalization. Under normalization, till now we have covered the concepts of functional dependencies, closure of the functional dependency set, finding the candidate key from the given set of functional dependencies, and the canonical form of a functional dependency set. And we shall be using all these concepts in the process of normalization. Now, let us take a look what normalization is. I have told you earlier also that normalization was proposed by Codd in 1972, and normalization, it is the process of taking the relations through a series of tests to certify whether a particular relation is in a normal form or not. And then if the relation is not in a normal form that we are looking for, then we follow a top down approach in which the relation is decomposed into further relations, which are then checked for the normal form we are trying to achieve. Initially, Codd proposed three normal forms: the first normal form, the second normal form, and the third normal form. And then he and Boyce, they proposed a new normal form called the Boyce-Codd normal form, also called the BCNF, which is a stricter form of the third normal form. All these normal forms, they are based on a single analytical tool which is called the functional dependency among the attributes of a relation. Later, a fourth normal form and a fifth normal form were proposed based on the concepts of multi-valued dependencies and joint dependencies respectively, and we shall be studying all these normal forms in detail. So, we said normalization, it is the process of analyzing and decomposing the given relation schema based on the functional dependencies, multi-valued dependencies, joint dependencies, and the primary key to achieve the desirable properties of minimum redundancy and minimizing the insertion, deletion, and the update anomalies. Unsatisfactory relations, they will go through the process of decomposition into smaller relation schemas that meet the test for the normal forms and hence possess the desirable properties of minimum redundancy and minimum anomalies. The normal form of a relation refers to the highest normal form that it can be decomposed to. So, let us take up the first normal form. Actually, the first normal form, also written as 1NF, it is considered to be part of the formal definition of the relation in the relational model. Historically, it was defined to disallow the multi-valued attributes, the composite attributes, and a combination of the multi-valued and the composite attributes. The first normal form, it states that the value of an attribute in a tuple must include only atomic, that is single and indivisible values from the domain of the attribute. So, for this reason, it is important that in the first normal form, in case any entity, it has a composite attribute like we have address over here, then all the atomic parts of the composite attribute, they are taken as the attributes like we have used house number, street, and city and pin code over here. We will not use address as an attribute which is a multi-valued, a composite attribute. Also, in the first normal form, it is important that any multi-valued attribute that is there, for example, locations over there, then for a multi-valued attribute, we always form a separate table with the primary key of the entity and the multi-valued attribute. So, that means in the first normal form, we will always have single atomic values as the values of the attributes in each tuple. Let us look at the second normal form, also written as 2NF, and the second normal form is based on the concept of full functional dependency. We already know that a functional dependency x to y means that x completely determines y, or y is dependent upon x, where both x and y, they can be a single attribute or they can be a combination of attributes. Now, a functional dependency x to y is said to be a full functional dependency if removal of any attribute A from x means that the dependency does not hold any more. So, that means if I have a dependency x to y, I remove any attribute from x, then if the dependency x to y does not hold, then we say that it is a x to y is a full functional dependency. On the other hand, if the removal of the attribute A, the dependency x minus A to y still holds, then we say that this dependency is a partial functional dependency. And like I said earlier, the second normal form is based on the full functional dependency. Let's look at this relation, which is SSN, PNO, Rs, ename, pname and plocation with the given set of functional dependencies. SSN PNO determines Rs, SSN determines ename, SSN PNO determines ename, PNO determines pname, PNO determines plocation, SSN PNO determines pname and SSN PNO determines plocation. Now, let us look at the dependencies one by one. In this dependency, if we remove SSN, then we are left with PNO determines Rs, but we do not have the dependency PNO determines Rs. So, that means removing SSN, PNO determines Rs does not exist. Similarly, removing PNO from here, SSN determines Rs does not exist. So, we can say we can neither remove SSN nor PNO in this functional dependency, and hence this is a full functional dependency. Now, let's look at this over here. If I remove PNO from here, I am left with SSN determines ename. I already have the functional dependency SSN determines ename. So, that means even if we remove the attribute PNO, SSN determines ename still exists, and hence this is a partial functional dependency. Similarly, over here, if I remove SSN, then PNO to pname still exists, and hence this is again a partial functional dependency, and in the similar manner this is also a partial functional dependency. So, through this example we clearly know what a full functional dependency and a partial functional dependency are. Now, a relation schema R is said to be in the second normal form if it satisfies the following conditions. It is in first normal form. Any relation schema will be in a normal form. To be in a normal form, it must be definitely in the lower normal form, in the previous lower normal form. So, a relation schema to be in the 2NF must be in the 1NF, and secondly, every non-prime attribute A in R is fully functionally dependent on the primary key of R. What does this mean? That non-prime attributes, they are fully functionally dependent, or in other words we can say that any non-prime attribute cannot be partially dependent on the key, or any non-prime attribute cannot be dependent on any part of the key. What are prime and non-prime attributes? Prime attributes are the attributes which form part of the key, and the non-prime attributes, they are the attributes which do not form part of the key. Now, the same relation which we had taken earlier, we have this set of the functional dependency, and if we calculate, we will see over here that SSN PNO is the key. How is SSN PNO the key? SSN PNO determines Rs, SSN determines E name, PNO determines P name, PNO determines P location. So, that means SSN PN ka closure, this is equal to R, and hence SSN PNO is a key. Now, R's, P name, E name, P location, they are the non-prime attributes, and the prime attributes, they are the prime attributes are SSN and PNO, they are the prime attributes. The relation is not in the second normal form. Why? Because of the functional dependency SSN to E name, PNO to P name, and PNO to P location. Why? Non-prime attributes are E name, P name and P location. E name, P name and P location. Key is SSN PNO. So, that means here the non-prime attribute, it is functionally dependent on only a part of the key. Key is SSN PNO. So, the non-prime attribute E name is dependent only on one of the attributes of the key. Similarly, over here the non-prime attribute P name is dependent on only one of the attributes of the key, that is PNO, and over here the non-prime attribute P location, it is dependent on only one of the attributes of the key, that is PNO. So, all these three dependencies, they are partial functional dependencies, and what did we say? We said a relation schema is in 2NF if every non-prime attribute is fully functional dependent on the key of R, or we can simply say no partial dependency exists. But in our example, these three partial dependencies, they are existing. Hence, we will say that the given relation is not in the second normal form. And what did we say? Earlier we had said that for any relation, we will check the relation given the set of the functional dependencies and the keys of the relation against the normal form, and in case the relation is not in the required normal form, then we will decompose the relation into newer relations, into smaller relations, and see if we can achieve the desired normal form. So, what do we do next? To normalize a non-2NF relation into 2NF relations, how do we decompose? Decompose the non-2NF relation into 2NF relations where the non-prime attributes are associated with only that part of the key on which they are fully functionally dependent. So, we are saying that the non-prime attributes, non-prime attribute are, they are associated with only that part of the key on which they are fully functionally dependent. So, ours is fully functionally dependent on SSNR and PNO. So, we form a relation SSN, PNO and Rs, and from the existing set of functional dependencies over here, we see the functional dependency in this relation or decomposition is SSN, PNO determines Rs, and if we try to find out the key, that is SSN, PNO closure, this will be equal to SSN, PNO Rs, which is equal to the relation, hence the key is SSN PN. Over here, E name is fully functionally dependent on SSN. So, we form the decomposition SSN E name with the dependency SSN to E name and the key SSN. Over here, P name and P location, the non-prime attributes, they are fully functionally dependent on the prime attribute or part of the key, that is PNO. PNO to P name is the function, PNO to P name and PNO to P location is the functional dependency here, and the key is PNO. So, now if we look at these three decompositions, we will see Rs, that is the non-prime attribute, is fully functionally dependent on the key over here. So, we will say there is no partial functional dependency, hence this relation is in second normal form. Similarly, over here the key is SSN, the non-prime attribute En is fully functionally dependent on the key. So, in 2NF, and similarly this relation is in 2NF, we have achieved the 2NF decomposition of the given relation, which was earlier not in second normal form. Now, it may be slightly difficult to achieve the decompositions like this. So, we use a simple algorithm which reads, let R be the relation schema not in 2NF, let F be the set of functional dependencies. First thing that we will do is determine the canonical form of the set of functional dependencies of R. What is the canonical form of a set of functional dependency? All the functional dependencies, they will have single attributes on the right hand side. There will be no extraneous attributes on the left hand side of any functional dependency, and there will be no extraneous functional dependencies. So, given the set of functional dependencies, we will reduce the set of functional dependencies to its canonical form. Then next thing we will do is we will determine the set of candidate keys for the given relation K1, K2 and so on. We will determine the non-prime attributes, and then these are the steps that we will follow for decomposition. That is, while there exists a non-2NF relation schema Ri, we do this for each non-trivial functional dependency. Means if we have a functional dependency x to y, if y is a subset of x, then we say that this is a non-trivial functional dependency. This we have studied earlier. So, for every non-trivial left irreducible, that means no attributes from the left hand side of the functional dependency can be removed. Functional dependency in Ri, if y, that is the right hand side, is partially functionally dependent on any prime attribute, that means there is a partial functional dependency, or x to y is a partial functional dependency, then we decompose our relation like this. Ri minus y means that the functional dependency, which is a partial functional dependency, then from the relation we remove the right hand side attribute of that partial functional dependency, union x y, that is the attributes of the partial functional dependency. What are we doing? We are trying to achieve this, that associate the non-prime attribute with only that part of the key on which they are fully functionally dependent. This is what we are doing over here also, right. So, this is the algorithm that we will generally follow for the 2NF decomposition of the relations which are not in second normal form. Now, let us take up this example. Check if the given relation R A, B, C, D, E, that means the relation R with the attributes A, B, C, D and E, and the set of functional dependencies A, B to C, D, A, B, C to E and C to E is in 2NF or not. So, from the algorithm we know what will we do. First we will find the canonical form of R, then we will find the keys of R, and after that we will check whether our relation is in 2NF, that is whether any partial functional dependencies are existing or not. Let us do it. Step 1, reduce the set of functional dependencies to a canonical form, that is decompose the right hand side, we get A B to C, A B to D, A B C to E and C to E. Checking for extraneous attributes, let us see, look at these two functional dependencies. If I remove A and B from here, I still have C to E. That means AB is extraneous in ABC to E. So, I get that my canonical cover is this FC is equal to AB to C, AB to D and AB and C to E, because this functional dependency is gone, right. Checking for the extraneous functional dependencies, looking at the given set of, looking at the canonical cover now, we see there are no additional or extraneous functional dependencies. So, this is the canonical form of our given set of functional dependencies. Step 2 is to find the key for the given relation. The key for the given relation is AB. How? Let us quickly see. AB closure is equal to ABCDE. How? AB closure is AB, AB determines C, AB determines D and C determines E, which is equal to the given relation, and hence AB is the key. If we check for C, C closure will not be equal to R and hence C is not the key. So, the key for the given relation is AB over here. Now, checking for the partial functional dependencies, AB to C, the non-prime attribute C is fully functionally dependent on the key, no partial functional dependency. The non-prime attribute is fully functionally dependent on the key, no partial functional dependency. Neither C nor E are the prime attributes. So, no partial functional dependency over here. Hence, we say that the given relation schema, it is in 2NF as no partial functional dependency exists. Let us take up this example again. Given the set of, given the schema A, B, C, D, E, F and the set of functional dependencies over here, determine if R is in 2NF, if not, decompose into 2NF relations. So, quickly we will find out the canonical form. We already know how to do it. Decompose RHS into single attributes. We have done this over here. Remove the extraneous attributes if any. Yes, in the FD AB to E, A is extraneous. In AB to E, A is extraneous because if I remove A, I still have B to E. So, the canonical cover is this, that is AB to E is removed. Remove the extraneous functional dependencies if any. There are no extraneous functional dependencies, hence this is the canonical form of the given set of functional dependencies. Next step is to find the key for the given relation. I will not repeat, quickly we will say key are A, B and C, because AB closure will be equal to R if you compute, and C closure will be equal to R if you compute. Hence, in this case the keys will be A, B and C. Now, if the keys are in A, B and C, next step is to determine if R is in second normal form for the given set of functional dependencies or not. Let us see. This was our canonical cover over here. The keys are A, B and C we computed as the keys. No partial functional dependency. C is fully functionally dependent on the key. No partial functional dependency. No partial functional dependency. C to A, no partial functional dependency. Left hand side is a non-prime attribute. No partial functional dependency. No partial functional dependency, again E to F, no partial functional dependency, but in B to E the partial functional dependency exists. Why? Because B is a part of the key and the non-prime attribute E is dependent upon a part of the key. So, there is a partial functional dependency B to E. So, what will we do? We will decompose this relation on the basis of the partial functional dependency B to E. How will we do this? Like we said earlier, we will say R is equal to R minus the right hand side of this. union B E. What do we get? A B C D F union B E. Now, if I call this as R1 and I call this as R2, let us see here. R1 is A B C D F with AB to C, AB to D, AB to F, C to A, D to B and C to D from the given set of functional dependencies. If we compute the key, then the key will be A, B and C. R1 is in 2NF, no partial functional dependency, no partial functional dependency, no partial functional dependency. C is the key, no partial functional dependency, no partial functional dependency. So, we say R1 is in 2NF. Similarly, R2 is BE, functional dependency from the given set of functional dependency is B2E and the key is B. Again we see that there is no partial functional dependency, hence it is in second normal form. So, we will say that R1 with the set of functional dependencies and R2 with the set of functional dependencies, they are the 2NF decompositions of R. Let us take up this example. Given the relation schema A, B, C, D and the set of functional dependencies, F is equal to A, B determines C, D, B determines C and C determines D. We need to see if it is in 2NF, if not decompose into 2NF relations, right. So, let us find FC, AB to C, AB to D, B to C and C to D. Let us look for extraneous attributes. If I remove from here A, B to C still exists. So, A is extraneous, we are done this with this. We are left with FC is equal to AB to D, B to C and C to D. So, now we have this as the canonical cover. There are no extraneous functional dependencies, hence this is the canonical cover. Let us find the key. If we compute the key, the key in this case will be AB plus, because AB plus ABD, B determines C. So, ABCD which is equal to R. So, the key is R. Now, let us look at whether this given relation it is in the second normal form or not. Quickly, AB over here there is no partial functional dependency, C to D there is no partial functional dependency, but a partial functional dependency exists which is B to C. So, we will decompose our relation based on B to C R minus C, that is the right hand side, union B C which is equal to ABD union BC. Here the functional dependency from the given set of functional dependency is B to C. The key is going to be B. From here, from the given functional dependencies, it is AB to D is the functional dependency and the key is going to be AB. Let this be R1, let this be R2. Both R1 and R2 they are in the second normal form because there are no partial functional dependencies. So, we say that the 2NF decomposition of the given relation R is R1 ABD with the functional dependency AB to D and the key AB, and R2 BC with the functional dependency B to C and the key B. So, this is how we can decompose our relations into the second normal form based on the key and the functional dependencies and the partial functional dependencies. These are the references for the topics that I have taught in today's lecture. Thank you.